ever see like I'm not pointing in the right direction or something, if you happen to notice that, just let me know. Oh. Okay.
Oh, let's see. You're going to be very excited about this. Quiz 2 is going to happen this Thursday. And you're all like, yeah, that's going to help us, Jeff. Thanks. Watch us all smile big now. It's going to cover the other civilizations, Babylonian, Mayans, and then other bases. Base 2, base 7, base whatever. You guys kind of with me? So if you've done, by Thursday, if you finish 2-2-2-3 homework, you should be completely ready for this quiz. So it's basically 2-2-2-3. The rest of 2-2, that's the Mayans and the Babylonians, well, referred to as maybe. And then 2-3 is the other bases, so it uses our symbols, but it has like base 4, base whatever. Okay. Maybe. All right. So, last thing with section 2-3 are these bases that are higher than 10. And it's very, the first hurdle we have to get over. If we did have an extra finger poking out of one of our hands, one little extra finger, one little bonus pinky here, we would have most likely had a base 11 number system. Why do I have a base 10? Because this. Do we know that for a fact? No. Is it a really damn good guess? Yes, right? This is the immediate thing about, well, why would we have base 10? Well, what's a natural thing to count on? What's right here? So what the shit would that mean? Well, okay, base 10, this is where we left off last time a little bit. What's the highest single digit we need in base 10? The symbol 9, right? Because the actual symbol for 10, of course, is one of our base plus no ones. That's why 10 means 10, because our base is 10. I like it. So base 11, it wouldn't roll over to this symbol. And so what would base 11 look like? There would be a ones place and 11's place. So what would 11 look like? What would the symbol, what would the number 11, what would the numeral be for it? I would have 111, 0 ones, correct? In fact, you guys with me? Why does 10 mean 10 things? Because I have 110, no singles. Yes? So if I had base 11, what would 10 mean? It would mean 111, no ones. So what is the number, how do you represent 4 in base 4? 1-4. Sure, 1-4, and so 10 is 4 in base 4. How do you represent 7 in base 7? 10. How do you represent 38 in base 38? 10. I really want you to get this. So base, what would base 38 look like? What places would it have? The ones place? 38's place, and then 38 squared, some crazy ass number. How would you represent what we call 38? You would have 138 and no ones, right? So why does 10 look like 10 in our base? Because our base is 10. I have one of our base and no ones. Are you guys semi with me? I like it. I really want you to start to understand the symbol 10 didn't have to mean what it does. It's because we chose our base to mean, when I get a complete group of what we consider 10 things, that's when it becomes 10. If it was based on 11, I wouldn't roll over until I got to 11 things. So, if we have base 11, I need single digit symbols. For 1, like we already do, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Do you understand that? For base 10, what's the first time I use 2 symbols to represent a number? When I hit the base, 10. So I need single digit symbols for 1, 2, 3, 4, 5, 6, 7, 8, 9, and of course 0. You guys all with me on that? Is everybody with me? So if we had base 11, we would have to go up to 10 for the single digits. I really want this to make sense. So if I had can you guys envision a speedometer, right? But if it's base 10, this is going to roll to 2, 3, 4, 5, 6, 7, 8. The minute it gets to 9, the next thing it does is it rolls over, correct? Because now it's got a full group of 10. Base 10 fundamentally counts groups of 10. That's what base 10 does. So base 11, so this would roll over to 1, 0. That would roll over. So base 11 would go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it would still need to have a single digit here because it would roll over when it got to what we call 11. It would need a single digit to represent the idea of 10 because it hasn't gotten a full group of 11 yet. How are we doing there? So again, we have a single digit 1, correct? We have a single digit 2. Base 3. What are the symbols for base 3?
0, 1, 2.
0, 1, and 2. It doesn't have a single digit symbol for 3 because it is base 3. How would you say 3 in base 3? What are the places in base 3? 1s, 3s. So how would you say 3 in base 3? 1, 3, no 1s. Yes?
So for base 11, would 10 be like R9?
Sort of, yeah. Yeah, R9 just means we're almost to a full 10, but it still has a single symbol for it, correct? It has to. The minute I have 2 symbols, that means I have some number of the base plus some number of singles, right? If I have 2 symbols, that means 1 base plus no 1s. So I can't have 2 symbols for base 11 until I get to the number 11. So all we do then, this is what we do. In fact, the book uses something silly, but I'm just going to use A. I think the book uses, like I said, T and E for 10 and 11. But hexadecimal uses A, B, C, D, E, F, yes?
So just to like conceptualize it better, for something like base 38, there have to be like 37 symbols.
There'd have to be 37 symbols, yeah. Okay. If we wanted to use our idea, so like Babylonians, how did Babylonians get around this problem? Like they're base 60, correct? So if they were using something like we do, they would need single-digit symbols for everything up to 59. But they didn't do that. How did they get around that? How did they represent the number 59? Do you guys remember? You can do it 2 different ways. You can have 5 Pac-Men and then 9 ones, correct? So they didn't use single symbols. They actually kind of built, which kind of led to a lot of confusion, correct? And you guys have experienced some of this confusion. Okay, maybe. So would you agree then that having a single symbol for a certain number of ones is better than building a single digit out of multiple symbols? So you guys agree with me? Okay. Which means there's a trade-off. If your base is base 11, you need a single symbol for the idea of 10. The same way, do we have a single symbol for the idea of 8? Yes. Do we have a single symbol for the idea of 3? Yes. Does base 3 have a single symbol for the idea of 3? No, they represent 3 as 1, 0. All they know is 0, 1, 2, and then it goes to 10. Do you guys get that? In base 3, 2 plus 1 is 10. Why? What does this mean? They mean 1, 3, no 1s. Correct? Do you see the comparison? We're base 10. So what's the number that comes right before it rolls over? 9. So that's why I liked when somebody said, is 10 like our 9? Because what's in base 11, what's the number that's a single digit and the next one is going to be 2 digits? 10, right? Okay, maybe. So watch, all this means, all this whole thing means is if I have, and by the way, the base 3 people, they would freak the shit out just as much as you are if I said to them, we need a single digit for 3. They would be like, what the shit? And we're like, let's use A. And you're like, why the shit? Right? They would have exactly the same kind of pushback. They wouldn't understand that. Because all they know is 0, 1, 2. That's the only single digits they've ever needed. And then they start to wonder, what if we had, instead of 3 fingers total, what if we had 4 fingers. What would that mean? Right? And students are like, why do that? Okay. So coming back to base 11. So now we have 0 means 0, all the way up to 9 means 9, and now A means 10, for example. So if you saw this number that's in base 11, if you saw 4A, base 11, how would you kind of parse that out? The A is in the what's place? One's place. And the 4 is in the 11's place. So the first thing I would do is write 4, get out of there, Jeff, thinking ahead. 4 11s. And what does 10, what does A represent? 10. So I really have 4 11s and 10 1s. That's all that means. And why do I need that? The same reason we need the symbol 9. We need the symbol 9 because that's the last amount of singles I can represent before it rolls over, right? Okay, maybe. So then what number is this really in our system? 4A base 11 would be 4 11s plus 10 1s, 54. So if some civilization had a base 11 system, and they happen to use our same symbols, 4A would mean 54 things. Okay, maybe. So just to kind of take a step back, help me out. If I have base 5, let's say I have 1, 3, 2, base 5, right? Base 5 is beautiful because it lives within ours. It lost some symbols. That's even better. It's got less symbols to worry about. Great. What would 1, 3, 2, base 5 mean? What places would these all be in? What's this place? 1s, 5s, 25s. Kick ass, right? You can always do that. Whatever the base is 1 base squared, base cubed, however long you need. Same way 1, 10, 10 squared, 100, 10 cubed, 1,000. Same way that base 10 works. So then you can piece together what that number would be in our system. Right? We'd have 125 plus 3 5s plus 2. So we get the answer to life, the universe, and everything. 42. There you go. I don't know if anybody gets that. No. I just like to see. No? Okay. So if we had a base 5 number system and somebody's like, you know there's going to be 42 people showing up. What we think of 42, they would write that down as 132. That's how they would represent the idea of 42. Is that cool? And again, it's really just, we chose groups of 10 to be special. We chose that. You guys understand what I just said? Somewhere in history, we chose that groups of 10 are special, and of course it makes sense because we see a group of 10 on our freaking arms. Like, this must be special. I got a group of 10 right there. So again, if we had 12 fingers, we would have thought of base 12 to be special. Baker's dozen if we had base 13, right? So maybe. So we would kind of roll over. Right now we roll things over when I hit a group of 10. In base 11, we wouldn't roll things over until we got a group of 11. Okay. So what do you think about base 16? You would have to use 0, 1, 2, 9. So it needs a single digit. How far up does it need a single digit for? The idea of 15, correct? How would you represent the number 16 in base 16?
1 0.
1 0. How would you represent the number pi in base pi? 1 0. There. 1 pi. No ones. Okay. Do you want to do base pi?
No.
Sounds like it should be great, but no. So then, of course, we use A for 10, B 11, C 12, D 13, E 14, F 15. So if I saw a base 16 number, 9 to E, base 16. what's the first step you would take to figure out what that is for us? What would that mean for us? What's the first step to take? Yes?
Write down what basic.
Yeah, what are the places? What are the places I see? So I would put 9 to E. Ones? 16s? No? 16 times 16. 256, I like. Okay. And again, you get calculator. You with me? So almost no matter what. So the symbols are weird. The idea is definitely weird. Again, why are you pushing back so much? Because, like I said last time, base 10 is so fundamental to everything we do. It's been something we've been exposed to since we could see and hear. We've been exposed to this idea. It's just so fundamental that when somebody says, oh, it didn't have to be that way, you're like, ah! So now I can just put this back together, right? So I have, how do I do this math? What do I do? 9 times, okay, 9 of these, plus 2 of these, plus how many of these? 14. Is that cool? And I really want you to see, if I just put the number 14 here, wouldn't it look like there were 4 places? If I put 1 4 right there instead of E, wouldn't it look like there were 4 places? Yes. Do you guys see what I'm saying? So if I put 9 2 1 4, and I was like, oh, I hope everybody knows I mean that as one thing. No, they're going to see 1s, 16s, 256s, whatever the shit. Right? 16 to the 3rd power. I'm sorry, yes. And then you.
How did you figure out that E was 14?
Up here. So we could have done almost anything. We just needed single symbols for everything up to the number 15. The same reason that base 10 needs single symbols for everything up to 9. Same reason. We just chose because, you know, we're not very creative. We just went, well, let's just use A, B, C. It could have been more exciting. We could have made totally new symbols. Like 11 could have been this symbol, and 12 could have been this symbol, or you know, offset that by 1. You guys, we could have made completely different symbols, but we didn't. We just chose to go A, B, C, D. Yeah, because it's easier. They're already on the keyboard. We didn't want to do a whole other set of keys on the keyboard. For example, yeah. Sorry.
Couldn't you just put a comma between each set of numbers? Like if you were trying to say that it was 9, 2, and 14, if you just put a comma between.
Yeah, you could have a civilization or something, a different alien to civilization that could decide to kind of group their numbers like that. But that's not how a place value system works, right? How does a place value system work? Single digit in every place. Now, to be honest, again, did the Babylonians follow that? Did the Babylonians do a little bit something more like you're talking about, sort of? Because they could put how many symbols in a single place? They could put a shit ton, right? I could have 5 Pac-Men and 9 ones. You with me? And that could all be in the single place because of how they built their system, correct? Okay, I like it. So, I love your question. Could have been any damn thing. Could have been, it could go up and down. We could have made diagonal. We could have made something that spiraled out. We could have made it based on colors. We could, and again, I told you guys, I think, about my Math 120 where I asked them to create their own number system. And I got some people that improved on our number system. It was fantastic. I got some kick-ass shit. And the thing that people don't understand is how much flexibility there is. I think I told you guys, somebody made it based on musical notes. Somebody else actually made it based on smells. Somebody made it based on the distance from Earth to a star was a certain symbol or something. It would actually, if you piece it together, that's the name of the star. It was crazy. So you're pointing out the flexibility. Great. We're talking about something rigid, though. We're talking about if it's a true place value system, it would require a single symbol to be in that place. Okay, I like it. I like it. You guys doing okay? Yes?
In the book, doesn't it represent 10?
Yes. Yes, they do. So for base 16, they use this. And I wish to God they would just use A and B for 10, but I think I told you guys in the book they do use T and E, but that's only if it goes up to base 12, right? Which is really silly. Why not just make it consistent, correct? So if you want to use T and E in the homework, as the book says, great. If you put A and B, beautiful. The real key to that is, what could it have been? It could have been anything, right? We could have started at Z, Y, X, blah, blah, blah. And then we would all know how to do ABC backwards and pass all kinds of tests. Okay. Maybe. All right, I like it. That was the last little thing in section 2.3. Let's do this. So how does it work the other way? I don't think we've done enough of those. What if I wanted to take, what do you got, Jeff? Let's just make something, see what happens. 4,312, and I want to convert that to base, let's say base 15, just to be different. So what the shit? So it kind of makes sense. We talked about this before, and we've done some problems. It makes sense that if going, the way we've been going is multiplying and adding, this way should be a lot of dividing and subtracting, because we're doing the opposite thing, right? What do the places in base 15 look like? Ones, 15s, 225, 3,000, 375. Does everybody agree that's going to obviously be too much? That would be this times 15. Just make sure you've gone far enough. Okay. Does anyone remember how to do this? We've done a few of these before. Yes? Yeah. So this place, how much of this number can it take care of? 3375 of it, right? So that place can take care of that much. I like to think of it like that. So if I subtract, I see how much the other places have to take care of. So let's see, what's that going to be? 933, no, 37? Is that right? Okay. And then how many of the second place and how many of this place do I need, and how much can it take care of, right? 4? Yeah, 4 would be 900, right? So now you got 37 left to take care of. So this is not going to be, well, let's see. Yeah, it might. No, it's not. Shoot, I didn't make a very exciting number. Sorry. So then 15, how many 15s? 2. 7. So in this case, we didn't need any special symbols. It was base 15. So you don't have to put a little 10 if it's our base, because we never do. We know it's our base. But if it's a different base, you better put what the base is. Is that cool? Okay, lock it. And notice real quick how this number is much smaller than this number. And it kind of makes sense because every place means more, except for the first place, of course. The first place is ones. Every place is able to take care of more shit, so it can represent really big numbers with a much smaller set of digits. Maybe. Okay. Now again, just to remind you guys, I don't know if I told you a story about, I wanted to teach algebra in high school. It's my very first kind of goal going to college. And so I think I told you this. I was really upset when they made me take calculus, because I'm like, why do I need to know calculus? I just want to teach algebra. And of course, until you take it, you don't know. So you've got to know much more than the level you're actually teaching at to be able to really teach that level at a fully give it a rounded approach of teaching. You have to know a lot higher level than what you're teaching. You guys all with me? Because I'll sometimes get a student in this class that's like, why are you talking about this shit? You're never going to look at this. And I'm like, I know. But you have to really understand how your own number system works, and what better way to figure that out than stepping outside of it. Does that make any sense? Okay. Yeah. Okay. Okay, let me see. I'm going to do one more example. Let me see if I can make one up real quick. That'll actually work the way I want it to. Tell me, what would base 13 look like? $21.97? Yep. That's enough, Jeff. Okay. Let me see. Let me do something real quick. Okay, so let's convert 38.99 to the base 13. So when you see a number without a base symbol, it's base 10. Same thing we've seen our entire lives. It's always been base 10. It's always been base 10. Now real quick, I kind of developed that number to do a specific thing. I would give you this number, you would write the places for the base it wants you to go to, and of course if you go in one more, it would be obviously too much. Does everybody see? And just to show you, if somebody didn't go far enough, what is 38.99 divided by 169? Help me out, somebody, just real quick. If I didn't go far enough, that's the first thing I would do, correct? What is 38.99 divided by 169?
23.
23, so they would put 23 here and think that everything was great. Is that okay? 23? There's no symbol for 23 in base 13, correct? So that would tell you you didn't go far enough in your places. Okay. So now let's do it the right way. Obviously, how many of these can I use? 1. So how much do I have left? Yeah, 1702. Is that right?
Yes.
Okay, now somebody got to see where I'm going with this. Make a little bit more interesting number here. So how many 169 is going to use? 10. You can see that pretty easily, right? So 10 of these suckers takes care of 1690, and that leaves 12, correct? Is that good? Are you guys with me? So this has got a double cool thing. So how many 13s? How many 13s for 12?
0.
0. Kick ass. Ryan comes in. Gah, we got this. So how many 1s? What's left over? 12. All right. Now this is not a good answer. This is the work still. We're still working it out. So within the work, we can use our own numbers because there's already enough shit going on without me throwing letters in the mix, correct? The last thing I do is convert back to the right symbols. But if you turn this in, it looks like this. The 1's place, the 13's place, the 169's place, the 2197's place, the whatever the hell the next place. That's way too big of a number, correct? Which is, again, another reason why we need a single digit up to 12 in base 13. So what symbol would go here? Yeah, so this would be 1A, 0, C, base 13. That's one Alexandria AOC, one AOC, I forgot her name. You know what I'm trying to say. Neato. Okay. So sometimes I like to play around with this and actually make little words and stuff, right? You can make the word cab and all that kind of stuff. Okay. Okay. So, you know, I'm not going to give you something like base 70 in this because then you would need how many single digit symbols up to 69? There's not that many letters, right? So that would drive you a little crazy. I'm not going to do that. Yes?
How did you get AOC again?
Oh, are you cool with 1, 10, 0, 12? Okay, 1 is 1. 10 is A. Remember? So like 0, 1, up to 9, and then 10 we have to use A.
Okay.
11 we have to use B. 12 we have to use C. So 10 is A, 0 is 0, 12 is C.
Makes more sense.
Because then I can tell I got 1, 2, 3, 4 places. And that's correct, yes? If I didn't replace this with a single digit, it would look like this is 2 places. It's supposed to only be 1 place. Does that make more sense as to why we need more single digit numerals? Okay, I like it. So the lower bases are kind of nicer because we're just using our own symbols that we're used to. Okay. So that's the last little bit of section 2.3. So what we're about to get into, and you know, I kind of joke around about it, but it's obviously when I ask algebra students what their least favorite part of math is, you guys probably would agree it's word problems. Does anyone agree with that statement? You do. Okay. You got a lot of company. Is anybody that's not true? Anybody have a different most hated part or least enjoyed part of math? Okay. Yes? What's yours? Fractions. Okay. Gotcha. So it's normally somewhere up there in the top is word problems, fractions, and graphing are normally the three big ones. Okay. So what we consider word problems is only going to be one small part of what we're going to do. What was the worst thing in the world is when you're in algebra class and you get the right answer, but you didn't use algebra. Has anybody ever had that happen? You understand what I'm saying? So you do the problem. The problem is blah, blah, blah. You're in algebra class, so you're supposed to set up an equation, but you're like, well, I can just tell it's 11 of these people and 12. So there's the 11 and 12. I can just tell, you know? And the teacher's like, minus 12. And of course it makes sense. When I'm teaching algebra, my example is if I'm taking a driving class and I say your final exam is to drive to the mall, and you walk to the mall and you call me, I'm here, do I pass? Should you pass the class? Of course not, because you didn't do the fundamental thing about the class, right? So if you solve a word problem using something other than algebra in an algebra class, of course you're going to lose points. So now we're looking at it a bigger step. We're looking at it in terms of what's the multiple ways I can use to solve a given problem. So what ways do you know? You obviously know use a variable. You know that part. That's from algebra. And there are certain problems that is the best approach to use. Would you agree with me that some problems that's not the best approach to use? If you were just allowed, just give me the answer. I don't care what you use. There are many problems you would not ever use algebra for. Is this correct? Yes. Yes? Of course. But I'm talking about like a word problem. Like Sally's got 8 apples and, you know, so forth. Okay. So let's do this. I want to talk about a few approaches. So the way that the book breaks this down, section 1.1 talks about several kind of general approaches to solving problems, and then section 1.2 kind of continues that list. So we're going to talk about a few, and then we're going to look at a few videos of kids solving kind of problems. And a few of those problems I'm going to ask you to solve before we watch them solve it, and so we can compare the way that we both approached it. So one of the most basic things, and this is the one that gets people in trouble in algebra, is the guess and check. And the book calls it, I agree, guess and check. The book calls it guess and test. But the guess and check approach, right? So let me see what you guys think about the guess and check. How would you guess and check if I said solve 4x plus 2 equals 10? And that one you can probably do in your head, but what would guess and test mean here? Yes?
Just inserting different numbers.
Yeah. Now, would you just randomly pick a number? Like, would you ever put 77 in there? No. So there's different levels to guess and check. I'm going to call it guess and check because that's the natural thing that comes. The book calls it, like I said, guess and test. So for example, you could pick 1. Does that work? No. And of course, if you pick 2, it does work. Okay, so that's the guess and test. So depending on the kind of problem, would you want to try guess and check for any equation? For all equations, I mean. Because some equations are going to have what kind of answers? Could 7 over 11 be the answer to an equation? Come on, come on. Of course it could. Here, what's the answer to this equation? Sorry, you're like, well, yeah, if you're going to do that. But I could make a more complicated equation where the answer is 7 over 11. Do you guys believe me? Okay, totally. Would you ever guess that randomly? If I gave you this long-ass equation, and you're like, let me just try, you're not going to go, yeah, let me try 7 over 11. No, you're going to try 2, 3. You might try some negatives. Yeah, you're never going to think to do 7 over 11. There's no way you're going to think to do that. So obviously, guess and check has a ton of limitations. It's not going to work on a lot of different problems. So the approach that we would not use for this problem, the first kind of level to this is just called the random guess and check, where you just truly just randomly throw stuff in there. Why would this one not qualify for that? Because like we said, you would know enough to not try 77. You would know enough to not try negative 100, right? Okay, maybe? So random guess and test is truly just totally just random numbers. Just throw it in and see what happens. The second level to this is called systematic. And this is something where you try, like we did, 0, 1, 2, kind of systematically trying to throw some numbers at it. By the way, just to let you know, we're back in section 1.1 now. So we're done with chapter 2. We're back in section 1.1. Okay. And then there's something called inferential. Guess and check. And this is one where you try to be a lot more prepared. You come in with an idea of what to even try in the first place. So, for example, let's do this example that's in the book here. I have circles set up like this, and I want to put the numbers 1 through 6 into circles, so that the sum of any side is the same thing. Let me make sure I got that right. Yeah, and actually we'll say it specifically has to be 12. So can you imagine doing it random? We're at least confined to 1 through 6, correct? But I can just randomly, I pick a number and put it somewhere. Can somebody come up, so you could just try to start filling stuff in and just seeing what happens. Let's do this. Systematic would be where you try putting a 1 and then just putting stuff in there. Inferential would be thinking about the implications of what you're trying to do. So for example, if you did put a 1 here, can somebody see where that leads to a problem? How many ways is there to add 1, 2, 3, 4, 5, 6. 3 of those numbers where one of them is 1 and getting 12. How many ways is there to do that? I want you to add 1 plus 2 other digits up there and get 12. How many ways is there to do that? How do you get 12? What 3 numbers do you add to get 12? 1 plus what? 1 plus 5 plus 6. Is there another way to do it? Is there another way to get 12 using 1?
1 plus 4 plus 7.
Is 7 up there?
Oh, no.
Good, okay. So the problem set I'm confined from 1 to 6. I really want you to understand what's happening. So if I put a 1 there, don't I have to get 12 twice? So if I put a 5 and a 6 there, that's great. Can I do it again? No. So what does that tell me? Can 1 be on any of the corners? So I know that 1 has to be in one of those circles. One of the inner ones. Do you guys see what I'm saying? Now how many times do I have to use 1 to make 12? Just once. So I'm using the constraints of the problem to kind of tease out the implications. Well, if I put this there, does that mess anything up? Yes. All right, so I don't put that there then. That's the highest level of guess and check, which obviously makes sense. It's the hardest level of guess and check, where you have to kind of predict what's going to happen or kind of tease out what's going to happen. So let's try to finish this up then. Well, so now what goes here and here? 5 and 6 is the only, and does it really matter if we put a 6 there or 5 there or the other way around? Because the whole thing is symmetric. I just turn it, reflect. It's the same damn thing, right? Okay, so now we're almost there. Think about 6. What's another way to make 12 using 6? Two and 3 and 6 make 11. 2 and 4, right? You guys kind of with me? So obviously, once you've got one part of it down, the rest of it's going to kind of become a lot easier because now it's a lot more constrained. Are you guys kind of following? Now again, let me say that I'm going to say this a few times. Getting the answer is icing. If you are unable to actually get the answer to any problems, your most important thing is to show me your thought process. And for students, this is really difficult. I need you to capture your attempts at an answer. Do you understand? You do not want to just erase something because it didn't lead you to the right answer, because that is actually work. You don't want to lose that. Does that make sense? The most important thing in Chapter 1, and any questions I ask you in Chapter 1 in a test or quiz, is showing me the approach you tried. Everybody with me? The answer is icing, right? So if you don't get the answer, but you show me all the work, you might lose a point. If you get the answer, but you show me no work, you're going to lose most of the points. Does that make sense? Because that's the whole point of this, is understanding the approach to problems, right? Okay. And I really want you to understand that, because some problems just require something to click. So if you're not lucky and it doesn't click, that's not nice. But that's why what you can control is the approach you take to a problem. Does that make sense? So as long as you show me you're trying a valid approach, you should be good. You should get most of the points. All right. So what do you guys think? So for 6, it would be 2 and 4, correct? Right? Or 1 and 5. Oh, we already got that. So 2 and 4. Now it comes down to, if you put the 2 in one of these, does it make a mistake? So now think about 5 now. So 6 is 2 and 4. What about 5? 3 and 4. So now you see that this 6 is 2 and 4. So they got to go in here, and 5 is 3 and 4. So now you can see what they both share. So where's 4 got to go? Because they both need it. So it's got to be here. So they both get it. Do you see that? And now you can put 3 and you can put 2. Now notice something. The innermost circles are the smallest numbers, and the outermost, the ones in the corners, are the highest numbers. That's really intriguing. So if I gave you a larger triangle, you actually could build off of the pattern we just saw here. Okay, maybe? Okay. So you guys look really excited. Okay. So that's the first thing. It's got 3 kind of sub-levels. So guess and check. It's got these 3 levels to it. The next, and let me point out, in the book they actually do a decent job. Look on page 10. They tell you when is guess and check good to use. So for example, it's good to use when there's a limited number of possibilities. That makes sense. So that's why if you're solving some really large equation, you're trying to solve for x, guess and check would suck, because what can x be? What can x be in an equation? What could x possibly be? Any freaking thing. That's not limited enough. You guys kind of with me? When we have that very small problem, that's definitely limited. I know the answer is not 77. I know it just by looking at it. I don't need to go that far up. I have a limited set of stuff I can throw in and try. Okay. I actually try to teach, no matter what the problem is, you might want to guess and check something just to get a feel for how the problem works. Just throw something at the problem and see what it would do, just to get a feel for how it kind of works. I don't know if this makes sense. So very often, you know, if you're like, Bob forgot how much money he put into his 2 bank accounts, but he made this much money. I'm like, well, just throw something in, see what you would do. When a student's taking algebra, because some of you guys are going to be teaching 7th, 8th grade, they're going to start taking algebra. The hardest thing for them to understand is that even if you don't know the value and we have to use an x, you could actually just kind of make a number up just to see what your brain does with the number. Okay, so for example, with true word problems, basically the worst part about them, and by the way, I'm going to talk a lot today if you haven't noticed. Next time I have a worksheet you guys are going to work on. And you have this long thing you're reading through, and you don't know how much money he had. Well, just take a minute and say, okay, what if Bob had $4,000? What would that mean? What would happen? And then your brain goes, oh, I got to multiply here. You guys kind of with me? So you give the x a value, you see what your brain does, and then you put an x there instead of 4,000, for example. Okay. So here's guess and check. The next thing should make sense, and it sort of goes along with this one too. The next level is draw a picture. To me, this draw a picture is really the first step in a lot of other types of problem solving. Do you guys remember problems like Farmer Joe wants to make fencing around his garden? He wants the length to be two more than two times the width. How much fencing does he need if the perimeter, whatever, right? So the first thing you would do is draw a freaking rectangle, just so you have a visual anchor to kind of like label, correct? So drawing a picture very often is the first step in a bigger problem. So an example they give, now let me ask you this, it's kind of cool because this is going to be on one of the videos we watch. Okay. So if anybody plays Tetris, the name of this kind of shape is a tetromino. You know, like dominoes. What is a tetromino? So that's where Tetris comes from. Has anyone never played Tetris? Okay. So you guys are like, all right, I don't know what you play when you have free time on your computer. One other shape would be something like this, right? You guys kind of with me. So a tetromino is 4 squares where all the squares are connected by a side. So both of those match, correct? So how many ways is there to make it? So would you agree that this would be the same basic idea as that? Those are the same idea, correct? Do you guys see what I'm saying? So you wouldn't count this. Can you guys come up with one more way to orient those to match the definition? They have to have where all 4 squares are connected by a side to another square. So they can be connected to multiple squares. Yes? Here, come on. You're like, damn it, why did I have to open that? Sweet, all right. Yeah, kick ass. So that's a valid one. That's a brand new kind of family of shapes, right? So you could have put that down there. Same shape, fundamentally, right? Can anybody come up with another one? And you're all like, now that I know I have to get up, maybe not. Even if you draw it big on your paper, you can just show it to me if you don't feel like getting up. But can anyone come up with another one? Or is that all? Is that it? Is that all of them? If you take this idea, does anybody have an idea? Take this idea one more step. Didn't this just take one of the squares and shove it down here? Well, keep going with that idea.
You can reflect it like that. So that bottom box on top, you get what I mean? Like,
This here?
yeah, and on the
But that's the same thing, right? But do you mean, do something with him. All right, so let me draw. See if you guys. Is that a new one? Is that what you're saying? I don't know. You're like, no, but let me go with it.
No, but that's an idea.
Yeah, but just taking this box and putting it here is basically the same shape. So reflection of it, or a reflection like this, or turning it around, same basic shape. That is a brand new shape, yes, especially because I can't draw well. I cannot even draw straight lines. What the hell, Jeff? Oh, Jeff. If anybody plays Tetris, that should look like a familiar shape. There's one more shape. Yes.
Just like
Big ass
square.
square. There, right? So this would be an example of a problem that's purely draw a picture. The way to solve it is to just start playing with pictures, correct? There's not a ton of these you encounter in a lot of math courses where it's just purely draw a picture. A lot of word problems, like I said, you draw a rectangle, you label it, you create your equation. It's algebra driven, it's not visually driven. Okay, maybe. Let me ask you this. Let's see. Yeah, let me think. Do I want to do that? Yeah, let me do this. Okay. So we got guess and check. We got draw a picture. Let me sort of kind of build up to the next one. I want you guys to think about this for a bit. Let me explain this. I think I got it. I think. Almost. You almost got it. There we go. Okay. I want a few different ways to count the total number of dots. The obvious, most basic way to do that is to just count them, correct? Y'all with me? So let's just all get that one out of the way. You just go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so it's 15 dots. Yay. So one way is just to actually count each one. Don't say anything. Can you come up with at least one other way to do it? And I'll give you an idea. Let me just say one word: grouping. This kind of problem to me is very interesting. Let me know if you think you have a way. You already helped us out with one thing. Ryan, what you got?
You could do all of them except for one on each side.
Okay, so like, oh, I see. So you could do this.
Yeah.
This. This. So you got 3 groups of how many?
5.
And 3 groups of 5. That's the idea of multiplication. 15 again. Now, of course, the right answer is 15. So anything you do has to come out with the answer 15. Anybody else have a different way to do it? Oh boy. Yes?
The way I copied your triangle onto the paper was drawing each corner first and then doing 4 in between each.
Oh, okay. So you say these are 1, 2, 3.
Yeah.
And then 4, 8, 12 plus 3 is, okay, sweet. Yeah, okay, go ahead.
So I did like the 6 times 3 and then minus 3.
Okay, so beautiful. All right, I was going to ask about subtraction. All right, everybody just hang tight. Let me do this again. Oh boy. Jesus, Jeff, okay. Okay, I think it's right. So then you basically did this. You did 6, 6, 6. And then you subtracted the 3 you counted twice, right? Beautiful. So this way is sort of like take care of these first. This one is take care of them twice and then cut one off, right? So I love it. I love it. Is that all right? You guys with me? So the minute you draw that and you start talking about how many different ways is there to count this, your immediate reaction is, what the hell are you talking about? You count them, man. But then there's multiple ways to sort of like break that picture up. Okay, I like it. Okay, so what if, let me take this one step further. This is where I always get in trouble. Here we go. what if I had a triangle where one side of it had n dots? Is everybody with me? Each side has n dots. How many total dots are there then? You've already come up with two valid ways. This first way is not really, the very first way we did it, why is it not really as great? Because I don't really have a set number of dots, really. I've got n dots, so to count them would be sort of weird. So what if we use the second way somebody did it? How many dots are there if I do this? How many dots is that? If there's n total, how many have I just circled? N minus 1. You guys all with me? Let me stop for a minute. Right? Wasn't there 6 total here? So when I circled this, I circled 5, right? So I'm going to steal that idea. So there's n minus 1 here, and then here there's how many? N minus 1, and then here there's how many? Oops, don't want to go that way. So then how many are there total? 3n minus 3. Kick ass, right? Or I could do it this way. N plus n plus n, that's 3n, but don't I have to subtract the 3 that I counted twice? Don't I get the same damn answer? Of course I get the same damn answer, because no matter which way you break it up, there's got to be the same number of dots. Yes? So now we're starting to talk about this idea of using a variable. And of course, one of the most immediate reasons you want to use a variable is if there's an infinite number or many, many possible answers, right? Which is what algebra was created for. Okay, so let me ask you this. What do you think happens if I add up 3 odd numbers? Will something always be true? So one way to start to investigate that, so the question is, can you prove what happens when you add up 3 odd numbers? Does the same thing always happen? So one way to kind of start is to guess and test in a way. Give me 3 odd numbers. 1 through 5, crazy. So what happens when you add those together?
9.
So 1 plus 3 plus 5, 9. Okay, so there's not enough to go on yet. Do we have enough evidence yet to figure out what the general thing? No. So let's try another. Somebody give me another completely different set of 3 odd numbers.
7, 3, 5.
Okay, totally different. I love it. So then that adds up to be 15. Do we have enough to start to think of a general idea? There's actually two things you could say, but I'll take one. Let's see. Well, let's try another one. Let me start us off. 71 plus,
15.
what did it say, 15?
Yeah.
Plus 9. How's that?
95.
95. So if I stopped here, you might say you get a number that's divisible by 3. Does that make sense? Is that divisible by 3? No. Well, what else are these numbers? They're all odd. Okay, good, good, good. Have we proven that the answer will always be odd? Is it possible we just haven't picked the right numbers that throw us off? Of course it is, because how many combinations can we make? A bunch. An infinite number, right? Kick ass. I love it. So, how the shit do we do this? Do you guys know, what's the idea of an even number? Just go with me for a minute. What's the idea of an even number? Idea of an even number. Can somebody just tell me, what's the idea of it?
It's 2 times.
Yeah, it's divisible by 2, correct? So like you're about to say, it's got to be 2 times some natural number. 2 times 1, 2 times 2, 2 times 3, those are all even numbers, correct? Okay, so I can represent an even number as 2 times some natural number. Is that cool? Remember, natural numbers 1, 2, 3. The things that came naturally to us. So what do you think about an odd number? Don't say anything. Just think about it for a minute. Let me help you out. It's not 3n. You can see very quickly that doesn't get you where you want to be. How's every odd number compared to every even number? Like even numbers 2, 4, 6. Odd numbers 1, 3, 5.
2n minus 1?
Yeah. So one way to do an odd number is 2n minus 1. Or 2n plus 1. They just have to be offset by 1. Is that cool? You guys with me? By the way, some people get a little confused because they see the number 2, but that plus 1, of course, right? So how far apart is every consecutive set of even numbers? 2 apart, right? 2 to 4 is 2. Odd numbers, 3 to 5, 2, correct? So that's why they both have the 2n piece. Okay. The weird thing about algebra is this is a specific odd number. It's the odd number that you get when you know what n is, correct? You guys with me? So n is just something we don't know yet. If somebody told us what it was, that would be an odd number. So this question is, if I add any 3 odd numbers, how many have I represented so far? I've just got one of them. What would another one look like? I love you guys. Don't give up. I know some of you guys are like, screw this. Why did I choose the letter N? Because well, actually, 2 reasons. It's a variable. I can use any letter I want to, but N is sort of like natural numbers N. But did it have to be N? No. So somebody give me another odd number.
2n plus 1.
2n. Let's keep this minus 1 thing going.
Or minus 1.
Yeah. So somebody else give me another odd number. 2q, kick ass. 2q minus 1. So now do you see we've got something we can work with? I've actually given myself something I can do something to. If I add those together, I'm going to add an infinite number of numbers together at once. That's what algebra is all about. So let's see, what can I actually put together up here? What can I actually add together? Yeah, the ones. So I get minus 3, right? And are these like terms? No, right? You can't, 2n and 2m, I can't put those together. They're not like terms. But I can do this. Well, let's see. Let's do 2n plus 2m plus 2q. Stay with me now. I'm going to do something a little bit weird. Well, actually, let me do this. Doesn't every odd number look like twice something minus 1? Isn't that what we just used several times? Every odd number looks like twice some natural number minus 1. You guys all with me? That's what we said. That's what they look like. So let me do this. I broke the minus 3 up. Now, can I factor a 2 out of here? Out of all these, can I take a 2 out? Yes. Is that double some number minus 1? You guys with me? This is double some number minus 1. So isn't this an odd number? So we proved that if I take any 3 odd numbers and add them, the answer is still odd. And we got a feel for it over there. It kind of makes sense that it would, but that didn't prove it. Okay. You guys got an appropriate headache from all that. So the last few minutes, I just want to show you a couple of videos real quick.